Very wonderful morning to one and all. Good morning, guys. All right. My name is Parveen, and I'm going to be the host for the day. Welcome you all to Cypher 2016. And yes, ladies and gentlemen, we're going to have 3 speakers for the day. We have the very first one, Mr. Lalit Sachan. We have the second speaker after the tea break, who is Mr. Hari Krishna R. And the third speaker, post-lunch, we have Mr. Rajiv Mukherjee. To starting off with the very first speaker of the day, ladies and gentlemen, we have Mr. Lalit Sachan, who's going to take you through the very first session, and the topic is Turning Lamps into Lions, Winning at Machine Learning Using Ensemble Methods. Well, ladies and gentlemen, Mr. Lalit Sachan is the co-founder at Edvancer, one of India's leading analytics training institute. He has over 5 years of experience in business analysis and is extremely passionate about decision making through data analytics. He has worked as a business analyst, handling end-to-end analytics projects in financial services, retail, e-commerce, amongst others. He is an expert on machine learning, predictive analytics, R, Python, and SAS. So, ladies and gentlemen, let's put your hands together and give a huge round of applause to Mr. Lalit Sachan.
Since we have quite peaceful hall for ourselves, let's start. Although if you talk about ensemble methods, there are a lot of details that we can go into, and it will not be possible to fit all this in a 1 hour thing. So what I've done here for this talk is I am focusing on the idea of ensembling, and we do go through few examples, but I have skipped on finer or rather unnecessary details that we can do without for this 1 hour session. Just a minute. Yeah, just to give you a quick preview of what this talk is going to be about. Essentially, we are going to, in one line, we are going to talk about how to combine your traditional models in order to make them better, or in order to get a better outcome. We'll start with discussing few individual algorithms that we use. Then we'll talk about how we can combine them, discuss the majority voting or simple averaging of individual classical algorithms that we use. Then we'll talk about something that I especially like, blending and stacking, and we'll spend a lot of time there. We'll also discuss towards the end of the session ideas on, or rather further things that we can explore now that we get acquainted with what ensemble learning is. We'll summarize the talk, and then we'll open the floor for question and answer. Starting with discussion on what we already do, the algorithms that we use: logistic regression, SVM, decision trees, random forests, and so on. Now, the focus that you need to understand here is that, take for example logistic regression. At the end of the day, you end up having a linear decision boundary, right? Let me go to the whiteboard. So if you have your feature space like this, and these are 2 different set of classes, when you use logistic regression, you get a linear decision boundary. When you use SVM, depending upon what different kernels you're using, you might end up getting some nonlinear decision boundaries as well. When you are using trees, you get decision boundaries which are parallel to XS, something like this, or combination of these. Idea here is that all of these algorithms end up extracting some, sorry, is this visible to everyone now? So if you could not see what I was talking about earlier, we did not miss much. I was discussing that these different individual algorithms extract different kind of patterns from the data in a different manner. Not only that, if you have, how many of you have at some point of time developed say boosting machine models or a random forest and so on? So it's not that random forest is different from logistic regression and so on. Within the algorithm themselves, if you choose some different hyperparameters, you end up getting different kind of models. Different choice of hyperparameters results in extraction of slightly, maybe somewhat similar, but slightly different as well, patterns from the data. And it's not just true for classification, true for regression as well. The idea behind Ensemble is to make use of all these patterns which can be extracted in a different way using different algorithms, to combine the power of all these differences and get something better out of it. First thing, as I said, we'll discuss simple majority vote. Although I'm not a big fan of simple majority vote, in fact the example that we'll walk through is somewhat discourages you from using simple majority vote. But it's a very important in the sense to set the foundation of your understanding of ensembling methods. Consider this: there is this real outcome scenario, and the real outcome is 1 for all the 10 cases or 100% cases. And there are 3 models which predict the outcome like this, and if you notice, all of them have 70% accuracy. If I instead, using these individual models alone, if I take a majority vote, so this here is 2 ones, the majority vote is 1, and so on. If I take the majority vote, now my prediction accuracy is 90%. Okay, so we considered 3 specific instances of such kind of models which will have 70% accuracy, and this is rather a too good to be true scenario. It doesn't happen like that. But still, let's try to generalize the idea. Consider, so there are possible 4 outcomes. If you are considering 3 models, all of them are making correct predictions. 2 of them are making correct prediction, 1 is wrong, all of them are wrong, or 2 of them are wrong. You will end up making correct predictions if you're simply taking majority vote when all 3 are correct, or when 2 out of 3 are correct. And the probability will be, because the model accuracy is 70%, for this it will come out to be 0.343 and 0.441. When you combine them, overall accuracy comes out to be 78%. It seems like if you are combining 3 models with 70% accuracy, you are guaranteed to have 78% accuracy if you simply take majority vote. Why is that not true? There are 3 possible cases. You can choose two different pairs of 2 models which will be correct. Yeah. So outcome is correct, correct, and not correct, 3%. Yeah. Okay. So why is this too good to be true? Yeah. Hello. Is this? Oh, sorry. Did not notice. How do I? Is this better? Yeah. Okay. So my question is, why is this not guaranteed to happen? Yeah, and it might not be simply working like this. I'll give you an example rather than get lost in probability calculation. Consider these. These are 3 other instances of the 70% accuracy models, you can see, right? And now when I take the majority vote, this does not improve the accuracy at all. It is still 70%. Why is this so? Because these models are highly correlated. Okay, so the focus shouldn't be on that if I just take majority vote, I'm golden and I'm going to improve my results. No, you should take majority vote of different models which are extracting different kind of patterns from your data. So let's summarize quickly what we have learned till now. So we should ensemble models which are less correlated, and you can calculate correlation with your usual methods. And another idea is that we saw that everyone gets to vote equally. All 3 models get to vote equally, or all 5 or all 10, however many you are considering, which need not be the case. You can modify this by say, increasing weights for models which you consider to be more accurate, and you would want them to be corrected only when many other models or classifiers are not agreeing with the one. For example, if I have, say, 5 different models, instead of taking simple majority vote, if this guy says the outcome is 1 and everyone else is saying 0, 1, 1, something like this, or maybe yes. So here, if you took simple majority vote, your outcome will be 0, or any binary class that you're considering. But if I say I'm going to give this guy weightage 4 and everyone gets weightage 5. So when this guy says 4, it's like having 4 votes with 1. And now the majority vote is still in favor of this guy. And that way you can specify different weightages for different models and get different kind of outcomes. So I'll quickly walk you through a particular case study. How many of you have worked with R before? And if you haven't, it's just syntax. Don't let the codes intimidate you if it doesn't make sense. It's just syntax. Focus on the logic. The idea should make sense to you. Okay? This particular case study is about a subscriber campaign data, and we want to predict whether, given all this information, personal information, financial indicators, and data related to how the customer behaved with respect to previous campaigns. Using all this data, we want to predict whether they are going to subscribe to some other particular marketing campaigns in future or not. There's a quick glimpse of the data. The kind of data that I mentioned, there is personal information, financial indicators, and the outcome is Y in there. What we are going to do is, let's break our data into 2 parts here, train and test. We are going to build many different models which are inherently different from each other. Some more so, some. For example, KNN. How is KNN different from boosting machines? KNN ends up capturing local patterns in the data because it is focusing on the neighborhood. GBN in general is to simplify a lot, it is nothing but collection of different decision trees where each subsequent tree is learning from the previous ones. And then is extra trees and random forest. How many of you have used extra trees in any of your projects before? It's very similar to random forest, just that consider a tree. When you're building a tree, at each node you consider all the variables and whatever many possible splits are there for each variable. What extra trees do, they do not consider all the splits. They randomly select few splits and then choose the best one in that random subset in order to split a node. This basically introduces more randomness in your modeling process and in turn reduces the effect of noise, reduces the overfit which might happen in case of random forest in few scenarios. Okay, and in many cases it has been seen to outperform random forest model. Yeah, but that's not universally true, so to say. So here ET and random forest or extra trees and random forests are not very different from each other, but yeah, slight difference will be there. Extra stands for extremely randomized. Then there is support vector machines, which again have very different take on extracting pattern in the data. And then there is this good old logistic regression model. Okay, the codes that you see here, these models could have been much better if you tune the hyperparameters. For example, I have taken for KNN, if you go back, for KNN I have taken value of K as 50. So there is some parameter that I just took. That doesn't mean this is the best value out there. You might have to do cross validation and find out the best value of K. Okay. Similarly, for GBM, there are many parameters to tune: how many trees you're building, how many observations can be there in a node, minimum number of observations, what is shrinkage, how big your tree could be. An idea is that it's better if the interaction depth is between 2 to 5, because idea behind boosting machine is to combine weak learners. Okay, if you increase this, you might end up overfitting your data, or might not end up utilizing the power of GBM as such. Those who have worked with R, I got lazy here and I simply used method equal to OOB. You shouldn't do that, and in fact you get a warning if you run this in R that you should choose method equal to CV. So if I will be sharing these codes, I'm not sure whether we'll be doing this through Cypher or not. So, but yeah, I'll be probably put this up in GitHub and you can access that. So for that, this suggestion that use CV here. When you use CV here, you'll have to make few changes in GBM function. Similarly, for extra trees and random forest, you can tune a number of trees that a forest or extra trees have, and number of variables that they are considering at each split. And there can be other hyperparameters also. For example, class weights is one which I have not mentioned here. For SVM, the cost, which is by default 1 in the package 1071 at least, and choice of kernel, whether you want to use radial kernel or polynomial kernel, and within that what should be the degree of polynomials and so on. So there are a lot of parameters to tune. Here I haven't, I've just taken few default options and built these models. One last thing before I move from here, that is, I have randomly taken, not randomly as such, I have taken some threshold here. This should, in this case I haven't determined using KS or some proper methods for finding out threshold. I've just taken some threshold, so you can improve it further by utilizing those methods. And then I simply combined all these predictors and in a data frame, and I calculated their correlation. You can see here that KNN especially is very different from other models because it focuses on the local patterns in the data, as opposed to other algorithms which tend to extract more general trend in your data. Okay, and as we were discussing that ET and RF, because they are very similar in the way they work, just that the split selection is randomized for extra reclassifiers. The results are highly correlated. Okay, so ideally I should have selected the models which are not so correlated and taken the majority vote. But here this is a simple function which takes an array of different outcomes and gives you the majority vote from there. This simply calculates, considering all the outcomes, calculates the majority vote. This, however, instead of passing the entire row, so let me clarify that, because the code doesn't look very pretty there. This is clear to everyone, this line, right? You are simply passing each row and you are calculating the majority vote, whatever the higher frequency outcome is. In second case, what change has what vector I'm passing to the function max frequency. If you notice, I am writing C rep x2 4 times and then everything else. So if the vote was like this, 0 1 0 0 1, what I'm doing here is, instead of passing this vector, this row for finding maximum frequency, I am selecting the second guy, repeating it 4 times, so it becomes this, and then I am combining everything else except this guy. So 0 0 1. So what gets passed is this. So this is where you have increased the weightage of the second model among all the models that you were considering. Of course, you can make it more sophisticated in the sense that you give different, instead of making a higher weightage of just one model, you can try different weightages of each model. Okay. The performance is not something you will be excited about. In fact, the majority vote, or rather